This talk is going to be by Amanda Folsom. Amanda Folsom is a professor of mathematics and department chair at Amherst College and specializes in number theory on modular forms, harmonic mass forms, and applications to combinatorics in other areas. She hails from North Shore of Boston and received undergraduate and doctoral mathematics degrees from the University of Chicago and UCLA respectively. Beyond Amherst, Amanda has held assorted positions at the Max Planck Institute for Mathematics, University of Wisconsin-Madison, Yale University, and the Institute for Advanced Study, Princeton. Amanda believes in the visibility of LGBTQ+ mathematicians like herself. She is a member of Spectra, was a joint mathematics meeting AWM panelist on queer families and mathematical careers, and has given numerous research talks, including some at LGBTQ+ math conferences. Some of Amanda's additional outreach involves research with undergraduates and women in mathematics, including her work as research project leader with the Women in Numbers program. Amanda will talk to us today about symmetry almost.
Thank you. Thanks so much to the organizers and the Brooks Institute. It's great to be a part of this conference today. So I want to talk about symmetry or almost symmetry. And I'm going to really start to paint the picture of the story I want to tell. I'm seeing something like that because it's the audio. Sorry about that.
Amanda, terribly sorry to interrupt, but we're having some trouble hearing you. Is it possible to move your mic a bit closer or?
Is this any better?
Much better.
Okay, sorry about that. So I was just saying thank you to the organizers and the Fields Institute, and really happy to be a part of this conference today. So I'm going to be talking about symmetry or almost symmetry. And ultimately, this is a topic in, I'd say, analytic number theory that I'd like to get to, but I'm really going to start from the beginning and try to paint the picture by way of certain analogies to start. And my goal here is really to give an accessible talk so that, especially so that those of you who have not thought about this topic before can learn a bit about it. So let's really start from the beginning and think about just in general, what is symmetry? We've all encountered it. We all can experience it in many different ways. Here are some pictures of symmetric things, places, constructs. And when I was thinking about how best to tell this story, I opened up the dictionary and looked at what the dictionary had to say about symmetry. And perhaps as expected, there were a few different types of definitions of symmetry. One has something to do with mutual relation of the parts of something in respect of magnitude and position. Another one talks about a harmony of parts with each other and the whole. We also have a lot of symmetry in nature. So here are some natural symmetric things, certain creatures, maybe even our own face is symmetric, or is it? And indeed, that's also a sub-definition of symmetry that appears in the dictionary. But when talking about natural symmetry, the dictionary says that with respect to natural symmetry, this is associated to a type of regularity and beauty of form. And that made me scratch my head a little bit. And I started thinking that, maybe this is somewhat subjective because, here are some perfectly symmetric natural creatures. Would you view these as beautiful or not? Well, beauty is in the eye of the beholder, isn't it? And symmetry might not also be exclusively visual. It might be something sort of less literal, perhaps like a harmonious relationship, such as this one pictured here between children, or maybe it appeals to another one of our senses. For example, we can find symmetry in music. But right, we're largely mathematicians in the audience today, and indeed that's also a primary subdefinition of symmetry. And mathematically, we might be thinking about position of points or parts of a figure with reference to a dividing line, or maybe a property by virtue of which something is unchanged by an operation. So here are some mathematically symmetric things, a fractal, a matrix, a particular function, a bijection. Okay. So let me talk to you more about this type of symmetry in modular forms and number theory. And I'll start by drawing a picture. So this is a graph of a function called the J function. I'm not going to tell you exactly what this function is right now, but let's just stare at the slide. And even if you don't know what this function is yet, you can probably agree that it possesses some symmetry properties. Maybe it even possesses infinitely many symmetry properties. So what you're looking at more specifically is just a particular truncated version of the upper half of the complex plane. So right in the middle of this truncated picture of the complex plane is the imaginary number I. I'm not sure if you're able to see my cursor, but if you are, it's hovering over I right now. Okay. And then right down here at the bottom is just the real axis, the boundary of the upper half of the complex plane. All right, so what's happening with this function? So it's defined on the upper half of the complex plane, and it takes values in C. So really, there's sort of too many dimensions to graph this like you would that simple function I showed a couple of slides ago. But we can graph, well, with some limitations, complex functions using colors, as you see on the graph here. So what you're seeing is the value of the J function at a particular point in the complex plane represented by a particular color and a particular shade of that color. So more precisely, we can characterize any complex number by an argument or an angle, and then a magnitude. And so using all of the colors of the rainbow, we can indicate these arguments, and then how dark or light that is will tell us how small or large an absolute value the value is. So, okay, what can we get out of this? I mean, maybe we can't exactly tell, for example, what is J of I, but staring at it here on this graph, it's red. So, okay, that tells us we're probably looking at some positive real number, and that's not too light. Maybe it's not too dark either. And in fact, right, J of I is 1728. And here are a couple other values for you to look at 0, J is infinity, it has a pole there, and at this root of unity, e to the 2 pi I over 3, J is 0. And you see a black hole at that root of unity here. Okay. So, all right, this is enough. Maybe it doesn't give us completely precise info, but it's enough to show us the symmetry properties possessed by this J function. This function plays a really important role in the theory of modular forms. It's been around for hundreds of years. All right, so what's going on with these symmetries of this function? Well, to explain it briefly to start, we would say that it's symmetric with respect to a particular tiling of the upper half plane that I've drawn here. So there are a bunch of sort of curvy triangles and, well, infinitely tall rectangles with curved bottoms. These regions that we see are called fundamental domains. And why have I shaded one? Because it turns out, and if you sort of dial back to the types of symmetries you saw on the previous slide, if you know the values of the J function in, let's say, this infinite gray rectangle that I've shaded, then you're going to know the values of the J function everywhere due to the symmetries it possesses. And really this rectangle, infinite rectangle here that I've shaded is not so important. That's a standard fundamental domain, but you pick any other one of these regions that you see and say the same thing. If I rewind a little and explain this by analogy before we get into the math under the hood, it's like some sort of magic puzzle piece in a jigsaw puzzle that you have when you have a fundamental domain for a modular form in hand. So if you know, if you have this one magic puzzle piece, you know, if you're doing a jigsaw puzzle at home, well, that's just one piece. That's all you've got, and it doesn't really tell you much. You have to keep going and put the rest of the puzzle together. But you know, imagine we have some really magic jigsaw puzzle that you have one piece, and that one piece tells you how to put the rest of the puzzle together. Okay. So, okay. What's really happening here is a group action. So if we look at the group SL2Z that we call the modular group, 2 by 2 matrices with integer entries and determinant 1, then this has 2 standard generators, T and S, for translation and inversion. And this group acts, in the sense of abstract algebra, on the upper half plane. We define the action of a matrix ABCD on a point tau in the upper half plane by Mobius transformation, A tau plus B over C tau plus D. So that gives us another point in the upper half plane. Short calculation to believe that that actually lives in the upper half plane and not the lower half plane, but it does. And for example, what does T do? It translates by 1 unit, your point, and S acts as a kind of inversion. And what's happening with this modular J function is that it's symmetric with respect to this action of the modular group on the upper half plane. Meaning J of tau plus 1 equals J of tau, and J at minus 1 over tau equals J of tau. And because these are the 2 generators, or illustrating the action under the 2 generators of SL2Z, then we know that J is also symmetric when we apply any matrix in the modular group. Here's a picture of what the S and T generators do to this gray fundamental domain. T translates it, S inverts it, and here are all sorts of other combinations, and you fill out the whole upper half plane this way. All right, so J is a modular form, and basically these infinitely many symmetries that J possesses is a fundamental property of a modular form. And they also have certain power series expansions that we call Q expansions in the standard modular variable e to the 2 pi I tau, which we just by convention denote by the letter Q instead of writing e to the 2 pi I tau, which is clunkier. So here is the start of the Q expansion. We also sometimes call this a Fourier expansion for the J function. And you can see what it looks like expanded in Q. Sometimes we may be able to write down modular forms in slightly different ways. Sometimes modular forms can be written down as infinite products. So here is a well-known modular form, a different one called the Dedekind eta function, and it can be written down as a nice infinite product. We might be able to write down modular forms as Q hypergeometric series. This is another way to write down 1 over the eta function up to a slight normalization. And this isn't a Fourier expansion, it's another kind of expansion. But I mention this because we're about to think a lot about Q hypergeometric series. They're a bit funny looking, perhaps at first glance. You have these sort of increasing 1 minus Q, 1 minus Q squared, 1 minus Q cubed, and so on, appearing in the denominator of the summands. So it's sort of a funny thing. But it turns out that there is really a lot of important connections between Q hypergeometric series and this symmetric modular world. So, all right, back to symmetry. Now that we have a sense of what modular symmetry is, let's ask the question, what about perturbing symmetry? I mean, if you make perturbations to something that's symmetric, does it remain symmetric? Well, obviously that depends on what you do. And asking that question, we could also ask, if there is supposedly some amount of beauty associated with symmetry, well, do you still retain that beauty when you perturb symmetry? So, all right, here is 1 over the Dedekind eta function written out as a Q hypergeometric series. And we know that that's symmetric in the sense that it's essentially a modular form. Well, I'm going to make a very small change to this Q hypergeometric expansion. I'm just going to take all these minus signs that show up and turn them into plus signs. That probably looks like a strange thing to do. On the other hand, it's possibly relatively benign. I've just turned minuses to pluses. So is this very closely related Q hypergeometric series still modular? Well, that's actually a really big question. It might look like a strange thing I'm doing. It might look like a small question I'm asking. This turns out to be a really old and complicated question. That function with minuses turns to pluses appeared in work of Ramanujan now just over 100 years ago. And he called that Q hypergeometric series f of q. And he wrote down a handful of other functions that were similar in shape. They had these Q hypergeometric expansions, and he called them Mach theta functions. Here's an actual page of Ramanujan's writing, and he's describing to Hardy in the last letter that he wrote to Hardy, and now 100 years ago, some particular property of these Mach theta functions. So let's dig into what he's saying. Well, if you stare at this function, you can see really just by staring at the summands that it has singularities at even ordered roots of unity. When q is -1, when q is plus or minus I, and so on. And Ramanujan is saying that actually there's some modular form called B of q that cuts out these exponential singularities of f, meaning when q asymptotically approaches one of these even order root of unity singularities, the sum or difference between this Mach theta function f and the modular form B is bounded. So in that sense, we have an understanding of how the Mach theta functions are close to being symmetric. They're asymptotically close to being a symmetric modular form radially towards roots of unity in this sense. Ramanujan didn't actually prove this, but he wrote it down that this should be true. Said another way, we've been thinking about the upper half plane a lot so far in this talk. Well, if we just look at what the map tau goes to q does, there's a correspondence between the upper half plane, which has boundary given by the real line, and the unit disk, which has boundary, the unit circle. So approaching roots of unity in the disk corresponds to approaching rationals in the upper half plane. Keep in mind rationals. We'll be thinking about these rationals as a type of boundary to the standard domain of a symmetric modular form as the talk goes on. Okay, so Ramanujan made this claim, but it really was a big question to understand in the decades following Ramanujan's death. He passed away in 1920, and this was one of the last things that he wrote down, how exactly the Mach theta functions fit into the theory of modular forms, which is very old and well established, and people were still trying to figure this out for many decades. So we finally found an answer to that question not too long ago, that these Mach theta functions they exhibit a modular symmetry, well, almost. So let's take a look at that. So Sanders-Wagers showed in his PhD thesis now 20 years ago that while the Mach theta functions themselves are not modular, they can be completed to form certain modular forms, but there's a little bit of a trade-off in making this happen. So the idea is that, you know, we take something that is not quite symmetric, the Mach theta function, but it has a really nice Q expansion. It's something that's holomorphic. And Zwagers explained how to really lose that, you know, that holomorphic property, some nice properties of that Mach theta function. But in doing so, you can make the function truly symmetric or modular. So more precisely, Zwagers showed how to add some non-holomorphic function to f such that the resulting sum is modular, but it's not holomorphic anymore. Specifically, what do you need to add? Well, you need to add something here shown by this, what we call a period integral of a modular theta function. So this is a non-holomorphic function. It doesn't have a nice Fourier expansion like f does, but still, this is the thing you need to do to add to f to make it modular. So it's a kind of non-holomorphic modular form. In fact, it turns out to be an example, all of Ramanujan's Mach theta functions do, to be examples of holomorphic parts of harmonic Moss forms. These are quite similar to ordinary Moss forms, but the theory being developed around these kinds of Moss forms is a bit newer, approximately 20 years old. And a number of folks have been building this theory in the last 20 years. Technically, here's the definition of a harmonic Moss form. I don't want to spend too much time on this, but they must transform like a modular form. That's what's happening in bullet point 1. They're annihilated by a weight K Laplacian operator. They're harmonic, and they have certain growth conditions and cusps that are required. So that was a huge answer to an important question that took 80 years to figure out how these Mach theta functions fit into the theory of modular forms. They turn out to be examples of holomorphic parts of harmonic Moss forms. Let's go back to what Ramanujan was saying about modular forms can be used to cut out exponential singularities of Mach theta functions as well. That really was not 100% resolved either. As I mentioned, Ramanujan didn't prove his claim. And so once armed with more theory of harmonic Moss forms, I went and looked at this question with Ono and Rhodes, hoping to try to resolve it using the theory of harmonic Moss forms, which didn't exist, well, until it has started to exist. So we started just computing what happens as we approach -1 radially from within the unit disk. What happens to that Mach theta function f? Well, it blows up as we expect it would. But in fact, if you add to it the modular form b, as Ramanujan claimed, then indeed it cut out that singularity, and it looks like indeed this sum is bounded radially. In fact, it looks like it's converging to 4. We tried that again with a few other examples, and it checked out. We were asking ourselves, what on earth is happening in general? What are these constants and where do they come from? And we were able to answer it here, that very specifically, what is this radial limit as Q approaches an even order root of unity singularity, this sum or difference between the Mach theta function f and the modular form b? It's an explicit, strange looking polynomial in roots of unity. Okay, so we were somewhat satisfied that we had an answer. We could really see this radial limit concretely and believe it's bounded, but what is that? That was the other half of the story. So it turns out that there is another kind of modular form lurking in the background. And May I just ask for a time check? How much more time do we have?
We have about 7 more minutes.
Okay, thanks so much. Okay. So remember that, right, radially approaching roots of unity from within the unit disk is in the variable Q is equivalent to vertically approaching rationals in the upper half plane in the variable tau. So, all right, again, let's try to think about these rational numbers as a kind of boundary to the domain, the upper half plane of modular forms. Zagier wrote down a type of modular form that lives on this rational boundary. And this emerged all right around at the same time when we were thinking about this, and it really felt like something to do with this newer theory of quantum modular forms might be behind the scenes. So here's a quote from Zagier's paper. Quantum modular forms are a type of symmetric, modular form that live at the boundary of the space, the upper half plane. They're defined asymptotically, and they have a transformation behavior a little bit different. So they're defined in Q instead of H. They take values in C, and well, they don't quite have total modular symmetry there. There's an error function that must be allowed for. More technically, you can write down the definition like this. Like ordinary modular forms, quantum modular forms have a weight. And if you look at this difference here, this modular difference, which you would expect to equal 0 if F was truly modular on Q, it does not. It extends to be some suitably continuous or analytic function in R. So this is the kind of modular error that emerges in the definition of a quantum modular form. Here's a picture of, well, just the real part of a quantum modular form. If you graph it, it's all over the place. This is an actual example from Zagier's original paper on the topic. But if you look at the difference between g of x and g of minus 1 over x, this sort of modular difference, well, you don't get 0, but you see that sort of chaotic behavior on the left smooths itself out. And that's the nice analytic behavior in R that, that one should expect to see with a quantum modular form. All right, so back to this radial limit picture. What is this funny sum in roots of unity, this funny polynomial in roots of unity? It turns out that that is a quantum modular form. What we're looking at here is the value of a quantum modular form evaluated at a particular rational. Specifically, this is the quantum modular form. It's written here as an infinite sum, and that infinite sum becomes finite when you plug in a rational x. So to summarize, and then I'll stop, what we showed actually by way of a more general theorem, I'm just showing sort of one special case of our theorem, we have a more general result that this radial limit, this asymptotic limit between a Mach modular form, a modular form, and a modular form is the value of a quantum. So we have 3 different kinds of modular forms related in one asymptotic identity, or looking at it in another way from the lens of symmetry, we have an almost symmetric function in the upper half plane being very close to a truly symmetric function in the upper half plane, this function b, in the sense that their difference asymptotically, it's some bounded value. And what is that bounded value? It's another almost symmetric value in Q. So this is a nice way to see different types of modularity related, and also a nice way to see different kinds of symmetry related all in one equation. So, right, again, there's much more to say. A lot of this has been generalized and extended since our original work. which again really was made possible by further developments in the theory of harmonic Moss forms and work of Zwagers and Brunier and Funke and so on. There have also since been a lot of interesting applications, including to other areas of math outside of number theory. I co-authored a book on harmonic Moss forms and applications with Bringman, Ono, and Rhodes, where we lay out a lot of this theory and applications where you can certainly dig up a lot more. So thanks a lot for listening.